be talking about feature selection. One thing that I may or may not have said but want to say is that when we use the notation Z to mean our transformed data, we will use the notation. So when we use Z instead of X, we will use V instead of W. I think I remember saying this, but I just didn't have a slide. Just for bookkeeping so that we can keep it all straight in our head. So even if we start out with D features, the size of V may not be D because we may transform to some different number of features, which will be the width of Z. Ali?
When we add a column of ones to X for the intercept, we change D?
Yeah, Ali asked when we add a column of ones to X in order to give us an intercept, do we change D? So I've been a little sloppy about this and don't really have a convention that I'm sticking with. I guess if I want to be very strict, I would say D is the original number of features, and when we add that column of ones, let's call it Z, but that's a bit too complicated because it's such a small change and such a standard thing. So we can call D the original number of features, but I may sometimes be sloppy and have D and D plus 1 mixed up. You can call me out on it if I do that, if you want. Okay, good. For you taking pictures, these are all posted, by the way. The slides are posted, the videos are posted, so there's nothing here that you can't get online. Okay. So we want to find the true model of the data, and we haven't defined it so precisely yet. But for example, let's say we believe that y really is generated by some polynomial function of our features x. And then we want to find the degree of the polynomial p, because what we looked at last time was we could change that degree, we made it really big, and we could overfit a lot and get zero training error or very low training error. We could make it small, and then we would get simpler models that could underfit. So how do we pick this degree of the polynomial? I think you hopefully already know the answer to this. Should we pick p based on training error? No, because it's just the same thing we've seen over and over in this course. Should we pick the decision tree depth, or should we pick all these whole bunch of things based on training error? And it's always the same story. No, because we can make the model arbitrarily complex, get zero or close to zero training error, and that doesn't mean we've actually learned something useful. That goes with this. Okay, should we choose P with the lowest validation error? So that's okay. It's not a horrible idea. It's not in the same category of ideas as should we pick it based on training error, namely horrible ideas. But it may not be that great, even so. And as an example, maybe the true model is a quadratic model, and there's always some noise added. So the true data came from a quadratic function of x plus a bit of noise added, and then maybe the model with the best validation error actually has degree 3, but just a very, very tiny coefficient in front of the cubic term. So that might not be that bad in terms of making predictions, and it might give the best validation error, but it still might not correspond to finding the true model. And so the theme of this week is going to be this sort of issue, which is dealing with complexity penalties. So we're going to spend the whole week on this, which is, can we mess around with our loss functions? Can we mess around with our loss functions such that we discourage overly complex models? And we're going to do it in different ways today, Wednesday, and Friday, but that's really what we're going to be doing all week. So as a starting point for that, what if instead of just minimizing our squared error, which I have on the slide, we just say, you know what, my loss that I'm going to minimize is my score plus p, where p is the degree of the polynomial. It's some non-negative integer or positive integer, I guess, usually. So what is that going to do? Well, you're minimizing this function. And if I make p larger, that thing goes up. So if I have two values of p with the same error, I'm going to prefer the one with the smaller value of p. You're basically saying, let me add this extra thing that just makes you a little bit happier when p is smaller and a little bit sadder when p is large. And it's not just for the purpose of tie breaking, but it's more of a smooth effect than that, which we'll be talking about. But this is the basic idea of complexity penalty. So complexity meaning complexity of the model, like larger polynomial degree, and penalty meaning stick the thing in the loss to penalize you for a complex model. Okay. Right, so a problem is how are we actually going to minimize this function? So, well, it's not even that we can't use the normal equations, but we can't really use gradient descent for this either, because p is a discrete variable, and we only talked about gradient descent optimizing in a continuous space. Any questions or comments about this general idea of penalizing the complexity? Liam?
Is it not just like another thing that you have to decide what the coefficient would be in the
Could you say that a bit louder?
Like, I'm assuming you have to have a coefficient for the p, because you can't just have like +1, 2, or 3, and the score is like in the middle.
Liam is asking, should we also have a coefficient in front of p? So instead of just +1, 2, or 3, should we scale that by some amount? Yes, we will do that, for sure.
How do you decide what that coefficient is? Another hyperparameter?
How do you decide what that coefficient is? It's just another hyperparameter. My favorite answer to almost every question I get. Okay. So, one way we could solve this thing, or minimize the loss, is we can just set p equal to 1. Now we can use the normal equations or whatever, do our usual fit, get the score, and then add 1 to it. Or we can set p equals 2, form the features, train in the usual way, report the error, and then add the penalty 2, 3, and so on. So we're kind of mixing discrete and continuous here. So we're saying, okay, we'll just do an exhaustive search over p, that'll be our outer loop. Set a particular p, form the features, train, compute the error, and then go back and say, well, I have the error and I'm just going to add this extra penalty, and then I can pick the smallest of these. And so, in words, this is saying, if you want to convince me to go from quadratic to cubic, you better decrease the training error by at least 1. Because if I'm worse, okay, I'm definitely out. But even if I only increase by a little bit, if it's not enough, I'm still going to prefer the lower degree polynomial. And yes, as Liam mentioned, it doesn't have to be 1, it can be some number. But that's the intuition for how this works. Connor.
Why in those equations is the two p's different? Like in the last one, it's like Z3 and then at the end 4. Is that?
Yeah, like Connor was just asking why is the Z index and the P, it's just a notation off by one thing, there's nothing to read into that too much. Masood?
Yeah.
Yeah, okay.
I remember that you said so we can multiply the sum by, for example, half, and it doesn't matter, it doesn't change the scenario.
Yeah,
But
right.
I think right now it somehow matters in case that
Yeah.
I'm adding by.
Yeah, so Masood is pointing out that I've been saying you can multiply it by 1/2, whatever, we don't care. 10 times the norm, 1,000,000 times the norm. So yes, this week we'll need to be more careful about that because there's now the left-hand term in the loss and the right-hand term in the loss. And so if we can scale the whole thing, it can be 1,000,000 norm plus 1,000,000 P. But we have to be careful about the scaling between them for sure. Yeah. Okay, so there's a kind of family of scores based around this idea, and as Liam suggested, we can pick some arbitrary coefficient, which we'll call lambda, and then more generally than P, we can have some number K representing the number of parameters that we're estimating, or degrees of freedom as it's also called. So roughly speaking, if I have more parameters that I'm estimating, my model is usually more complex. And in this case, the correspondence is pretty straightforward. When we increase the degree of the polynomial from 5 to 6, we need one more parameter, which is the coefficient in front of x to the 6 that we didn't have before. But in general, it's a useful way of thinking, this idea of thinking about complexity in terms of number of parameters. And of course, I could make a case up where that's not true. Like, I could just have a whole bunch of parameters that are multiplied by 0 or not used at all in prediction. So I could make up a ridiculous case. But typically, this is a reasonable intuition. And so I said this earlier, lambda controls how much you want to penalize for complexity. So I need to, if I'm going to add another parameter or another degree of freedom or maybe another degree polynomial, I need to decrease the training error by lambda. So if lambda is huge, you'll be very reluctant to add another level of complexity because you have to basically pay lambda in this currency of the loss function, and it's going to be hard to earn that much. You have to decrease the loss by that big amount. Whereas if lambda is very tiny, in fact, in the extreme case, where lambda is 0, we're just back to what we were doing before. Just look at training error. So we can just throw away this thing by setting lambda to 0. As long as it's greater than 0, the effect is there. And when lambda goes towards infinity, then we say, actually, I'm never going to improve by infinity. So I'm just going to pick the least complex model available to me, maybe a degree 0 polynomial that's just the horizontal line. And I don't even care what the training data contains. So the two extremes, in a sense, are I only look at the data and try to fit it as well as I can, that's small lambda, to I don't even care what the data tells me, I just want the simplest thing possible, that's huge lambda. All right.
Nice. Can you make the lambda the left-hand side of the plus so it changes at every, like it's 10% of the error?
Can you make lambda a fraction of the error?
Yeah. So it would not be constant between the levels. It would
So that's sort of an adaptive method. So we're not going to talk about anything like that in this course. There are all kinds of fancier things you can do. We will put a little bit of effort later into thinking about how they compare, probably on Wednesday. Okay, so you may have heard from your statistics course or somewhere of the AIC, or some of these other criteria for deciding model complexity. And these are all part of this family of I'm penalizing by some amount, and if I pick lambda in specific different ways, then I have different names. Okay, so what's going on here? That was roughly okay. So in addition to AIC and some of these other criteria, there's also the BIC, Bayesian Information Criterion. Again, you may have seen this in some statistics course, or maybe not. But with BIC, we're going to pick lambda to depend on n. And so as n goes towards infinity, as we collect a lot of data, you can prove some things about this BIC. We're not really going to go into where this comes from. We'll only have one other lecture in the course really talking about probabilities and vaguely Bayesian notions.
Wait, sorry, the top statement, the disadvantage, blah, 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 it's from the previous, like using AIC and all that. Okay.
Okay, so, right, so Fed's question was, this disadvantage is referring to the previous slide. So, now going back to the original discussion with Liam, there's a whole bunch of ways that we can choose lambda, but in the style of how we're used to doing things, we can just say, oh, well, it's another hyperparameter, and we can also pick it based on cross-validation or a validation set, because lambda is supposed to help us generalize, and cross-validation is exactly telling us an estimate of are we generalizing well, so why don't we just pick the lambda that works for us. Okay, that is sort of the end of, I guess, motivation for this week and tail end of stuff we were doing last week. So this idea of penalizing complexity of models. Now we'll talk explicitly about feature selection for the rest of today, and we'll try to relate it to this idea of penalizing complexity, and that will also relate it to the rest of the week. Okay, so you may remember from the beginning of the course this food allergy example with decision trees. You record what you ate, you record whether you got sick, and you want to be able to predict whether or not you got sick based on the food you ate, in other words, based on the features. So, as I think I've said before, this course is very heavily focusing on prediction, meaning the task we really focus on in this course is get me something that, given a new x, I can predict the new y. And today we'll just deviate from that a little bit, which we don't do very much of, and say, what about this other question? And in the food allergy case, the other question actually makes a lot more sense. Because it's not really that I'm going to say, hey, algorithm, I was thinking of eating this tomorrow. Can you tell me whether or not I'm going to get sick? Yes. Okay, well, I guess I'll try eating this tomorrow instead. Am I going to get sick? Yes. That's not really how you would do this, right? What you actually want is a algorithm tell me what makes me sick and then I can just stop eating it, or maybe what combination of stuff, or maybe some amount of something. But it's more of understanding what the features are that cause me to get sick, and cause is kind of a dangerous word because it's very hard to infer from data what causes what, but at least what features are relevant in predicting or understanding whether or not I'll get sick. So for example, if I knew that the same data set minus the peanuts column was just as good at predicting as with, then that actually tells me something about peanuts, which is probably this is not the thing determining whether or not I get sick, because if I threw away that information, I was just as good at predicting. So there is this interplay between prediction and interpretation, inference, understanding, and we will do that dance a little bit today. Okay, so the general problem of feature selection is find the features, or in other words, the columns of X, that are important for predicting Y. So there's a bunch of reasons why this might be an interesting question. You might want to know what the relevant factors are. We just talked about that with the food example. You might have a whole bunch of basis functions, and you might want to know which ones are relevant or useful. A pretty important one, which again we don't talk about much in this course, is what kind of new data should I collect? So maybe I collect a little bit of data, and then I'm going to go do the real thing, collect the real data set. Or maybe I'm building some sort of machine that has 20 different kinds of sensors on it. And every time I sell one of these machines to someone, I'm losing a lot of money because I'm paying for these 20 sensors, and I'm saying, actually, which of these 5 sensors are actually useful for doing what the machine is supposed to do? Let me not include all the rest of them in my product, right? So in this course, we kind of assume someone hands you the data set, but just keep in mind that often you're kind of actively or collecting data in real time, or you may have some data, but then you're going to go do this very expensive process of collecting a lot more data, and you want to know what's actually worth going after. Finally, it might just be a computational issue. Maybe your system needs to operate really quickly, and you have a billion features, and it's just too many, and you say, in order for this thing to be fast, I can only support 10,000 features, so let me do that. Find the 10,000 features that are the best. So this is going to be messy, and the problem isn't even that well defined. Again, it's not that clear what is a good feature to select, but we're just going to assume for today that it's a feature that helps us in prediction. So any questions on the overall goal here? Connor?
Is the goal then to find the features that are like relatively the most important, or like absolutely the most important?
Connor asks if the goal is to find the features that are relatively or absolutely more important. So what do you mean by that?
Well, relatively is in like the most important features of all the features given. That, you know, like, are we looking for like the best predictors in the set, or are we looking for like the predictors that actually like do something?
Yeah, that's an interesting question. So we're going to look for the features that, given the ones we have, we're only going to keep some of them. Which ones should we keep? And I guess you would call that relative.
Yeah.
But it's a good point that, and we may get to it today, it's a good point that you might have a great feature that's very, very useful, but say some other information, it relies on being joined with some other information that I don't have, and so it looks useless and I throw it away. And that's simply a problem that we have to worry about. Okay, so a pretty common way of doing this is, let's just figure out the association or correlation between each feature and our outputs. So we take column number 1 and compute the correlation with y. We take column number 2, compute the correlation with y. And if the correlation is 0, it tells you that going up or down in this feature doesn't really tell you if I'm supposed to go up or down in y, so maybe it's not that important. If the correlation is very high, like 1, close to 1, it's saying this feature tracks y very, very closely, and if that's the case, then it should be useful in predicting y. So there's a branch of feature selection based on statistical hypothesis testing that we're not really going to go into, but it's worth knowing that such a thing exists. This particular approach, just looking at the correlations, is a problem because it looks at each feature independently. It doesn't take the context of the data set, and this sort of relates to Connor's question as well, in the sense that, let's say there's a great deal on tacos every Tuesday, and tacos are the thing that make you sick, or some ingredient in them, or maybe just that you have so many of them because they're so cheap, or whatever. But you're also recording the day of the week as a feature, and so you may find that the day of the week has amazing predictive power. Like, you get sick every Tuesday and you don't get sick. And then, yes, sure, you can now predict based on the day of the week, but we haven't achieved what we really want here, which is to understand why this is happening. And if we were to then collect more data, including Tuesdays in which the sale was not on, or some other day in which you had tacos, you would do a very bad job of predicting. So another issue is, I don't know, those of you who have seen videos or done it firsthand, this Diet Coke and Mentos mixing, but it was a popular thing when I was a kid. Anyways, mix them together, they kind of fizz up and explode a little bit. So say that makes you sick. If you have Diet Coke on a bunch of days by itself, and you have Mentos on a bunch of days by itself, then they might not look like they're relevant at all. Oh, let me just throw away that feature because it's not really correlated. Let me throw away this other feature. But together, they're actually very strongly predictive. So this association approach is just looking at one feature at a time, and so we actually miss out on a lot of useful information. Any questions or thoughts on this? What's your name?
It's Yushen.
Yushen?
Right. So I was thinking, can't you just walk through the decision tree, reflecting all the labels, and those would be the ones that are relevant?
Okay, so Yushen is suggesting, why don't we fit a decision tree and just look at the variables we split on, and then use those as our selected features. So it's an interesting thought. If you were going to then fit a decision tree, I guess that would be just as good as having the whole data set, because those were the only features we were going to look at anyways. Today we're going to focus a little more on linear regression specifically, and how to do feature selection there. And if I think of anything else intelligent to say about your suggestion, I will do so when the time comes. Okay, so as I mentioned, let's talk about linear regression specifically. I was telling you last week, and before that, we had this interpretation of the coefficients with linear regression, which is that if W3 is 7, then that means with feature 3, if I increase that value by 1 unit, then I expect Y to increase by 7 units. So it seems then that these regression weights are kind of doing feature selection for us. But we'll have to be a little bit careful here. So here's a suggestion. Let's fit a linear regression, and then just throw away all the features where the W's are small. So one appealing thing here is we're actually simultaneously looking at all the data in order to make this decision. Whereas before, when we just did the correlations one by one, we were making each decision without even looking at the rest of the features. And so you could actually figure out that this Taco Tuesday issue, and we talked before about collinearity as well, that if two features are exactly identical, then we don't know how to allocate the weight between the two features. And that's true, but if you have 95% of your tacos on Tuesdays, and then that basically, you can maybe break the tie then already. So you can say, well, all the other times I had tacos not on Tuesday, I also got sick. So you might hope that the regression weight ends up in the right place. And as you collect more data, there's better hope of that happening. So this can deal with the Taco Tuesday issue. If you have enough data and if the relationship is actually linear. And it could figure out this Diet Coke and Mentos issue as well. We're leaving a bit of details out in terms of how exactly am I doing the linear regression. But as I mentioned, if the Taco and Tuesday variables are actually identical, we still haven't solved this problem. And we talked about this before. I might also learn crazy weights. So this is more of a general issue with linear regression and collinear features. But now it's when we're trying to use this for feature selection, it really becomes a big problem. So one of the main things we're going to do on Wednesday is solve this issue now that it's already been weighing on us for at least a week. And when we solve this issue on Wednesday, we'll do better both in terms of prediction and also in terms of using this for feature selection. So stay tuned for that. So a very common method for selecting features is search and score. And the way it works is that we define some score function that tells us how good is some set of features. And then we just search over possible sets of features. Okay, seems reasonable. So say we have 3 features and we've decided on some reasonable score. We can try feature 1, 2, 3, and then all the combinations. So I won't read them all out, but if we have 3 features, there's 2 to the 3 possibilities. For each feature, I can either use it or not use it. So the total number of possibilities is 2 to the d. And I can just do this and find the one with the best score, and that's great on the slide, but I would need a very long slide if I was going to write this down for 100 features. We already talked about this issue of using the training error as our score. If we use the training error as our score, the more the merrier. Just give me all the features. we talked about that earlier in the context of polynomials, but in general, why not? If I'll take all the features you're willing to give me if I'm just trying to get a low training error. So validation error is an okay way of doing this. And we talked about that earlier as well. But there's this problem I mentioned that, well, there's two problems with this 2 to the d relationship. One is there's just way too many things to try out if d is large. And furthermore, if I could actually try out that many things, then we get back to this issue of optimization bias that we talked about at the beginning of the course, that if I'm trying a million different models on my validation set, then I may get some good results due to luck or randomness or some non-meaningful reason. By the way, it's very important that it's clear where this 2 to the d comes from. So maybe I'll just reiterate that. We start out with d features, and we're trying to select a subset of them. Another way of phrasing that is for each feature, I can either keep it or not keep it. So you can say, like, I'm going to write down a 1 or a 0 for each feature, and then how many possible subsets of features are there? It becomes the same question as how many binary strings are there of length d, which is 2 to the d. So I have 2 choices per feature, d features. Edwin.
When we use validation error as a measure of goodness, how many features do we use to train the model?
Edwin says when we use validation error as a measure of goodness, how many features do we use to train the model? So the whole idea here is that I'm comparing different possible subsets of features. So for example, I just want to know how good is keeping feature 1 and 2 and throwing away feature 3. That means use feature 1 and 2 to train the model and then compute the validation error, versus use only feature 2 to train the model and compute validation error, versus use only feature 3 and compute validation error. So the number of features I use to train is just however many there are in that subset that I'm considering. So now we're going to come full circle again a little bit and revisit this specific idea we talked about at the beginning of today, which was penalizing the degree of a polynomial or the number of parameters, and say, let's apply this to feature selection. So let's take the size of S, meaning the number of features, and have that be our penalty. And when we're talking about linear regression specifically, or say the polynomial thing, then the match is kind of perfect in the sense that when I add a new feature with linear regression, I need a new W for that feature. So each new feature is one new parameter. And so it's really the same thing, penalizing by the number of features or by the number of parameters. That's not true in general. It's not true that every model in the world has one parameter per feature, and we'll see many examples where that's not true, and we have already. But for linear regression specifically, the connection here is very strong. So all the intuition from earlier today carries over here. If we have two choices with the same error, we'll pick the one with fewer features. We were saying earlier, if we have a tie, we'll break the tie by the one with less complexity. But really, when we're dealing with linear models specifically, fewer features is less complexity. So everything, all the ideas kind of work out. Should I add this new feature? Well, does it reduce the error by 1, just like we talked about earlier? So what kind of appealing about this is if we were going to have some really tiny w, like 0.00001, that might help a tiny bit with training error, and that's what we talked about earlier with the quadratic and the cubic. But it may be worth throwing away that feature, making this score happier by 1, if it's only a tiny change in the training error anyways. So we're basically saying use as many features as you need, but try not to use extra ones that don't help that much. And then, as a notation issue, instead of saying the size of S, we can use the L0 norm as a way of writing this. I'll get to that in a minute. So because we're talking about linear models right now specifically, if I say set this W to 0, set W10 to 0, that's the same as saying remove feature 10. And again, this is specific to linear models. But with linear models, we just have that particular W multiplied by that feature, plus the next W multiplied by the next feature. So if I said W2 equals 0, that means 0 is going to be multiplying by feature 2 every single time. And so whatever feature 2 is, it doesn't matter. It's as if I threw it away. So again, for linear models, setting the coefficient to 0 or throwing away the feature are pretty much the same thing. And so the L0 norm, I'm putting in quotes, it doesn't satisfy the true requirements. You need to be an official norm, but we'll write it in the same way with the bars and the subscript 0. The L0 norm is the number of non-zero elements in a vector. So for example, if I have this vector on the left, then the L0 norm of it is 3 because I have 3 non-zero elements, and the L0 norm of the 0 vector is 0. So we can write the thing we had before with the size of S. We can write it like this because size of S was the number of features we're using, but we just said using a feature and W non-zero are basically the same thing. So L0 norm of W is basically the same thing as the number of features we're using. Ali?
Out of curiosity, like where does the L0 norm come from? Because we usually define the pth norm as like the pth root of all the elements to the p. But what's the 0th root?
The question is, where does the L0 norm come from? So I think if you make p very small, then it should hopefully approach something like this. But I need to think about that. Yeah. Okay, so we want to take, for example, just keep features 1 and 2. We fit W using those features, compute the training error, and then add lambda multiplied by 2, and then we repeat this with all the choices. So all things we've already discussed. Okay, so the idea here is we're balancing our squared error with number of features. We're using a complexity penalty in the sense that we talked about it at the beginning of class. And all the same stuff that I said before again applies. So lambda equals 0. We're back to good old least squares with all the features. Lambda towards infinity. Then all we really care about is that second term because it's infinitely more important than the data fitting term. So I'm just going to set W to be 0 and try to make that right-hand term happy, and I'm not even going to look at the data, and then everything in between. Okay. So it's all just the same kind of thing, but specific to linear regression such that selecting a feature or non-zero W are the same. Okay, so there's this other problem that I haven't addressed here. One problem was training error was no good. We solved that with this complexity penalty. The other problem is this 2 to the d. I don't want to try 2 to the d different things. So just like with decision trees, we had too many possibilities. We weren't going to try them all. Let's just do some greedy version. So we'll compute the score, baseline score, using no features. Then we'll try, I'm just going to add one feature. So all the possible first features to add, I'm going to try them, compute the overall loss, and then whichever one's best, I'm going to add it in. Now milk is in. Then I'm going to look at the remaining ones. Try adding each one, see whichever one is best, add it in. I'm just going to keep doing this until adding a new feature actually doesn't improve the loss. And again, that's only going to happen because we have this complexity term. If it was just training error, you would keep adding them forever. Okay, so pseudocode for what we just talked about. Is here. So like with decision trees, this isn't perfect, but we cannot possibly search over 2 to the d sets when d is any kind of reasonable number. I don't have time for your question, sorry, Ari. Okay, so we talked about complexity penalties at the beginning today. We started with the context of polynomial basis, and we said, why don't we penalize using a larger degree? Then we generalized that to this idea of degrees of freedom or number of parameters, and there's a whole bunch of different flavors of that for different values of lambda. Then we talked about feature selection and a whole bunch of different approaches with pros and cons, the correlation approach, fitting a regression model approach. Then we talked about search and score, and then there was a whole bunch of moving parts here. We decided to go with the complexity penalty just for the same reason as before, that otherwise we would add all the features. And we really made this equivalency between more features and more complexity, and furthermore we made this equivalency between including a feature at W being non-zero, which was specific to linear models. And then we talked about this greedy forward selection algorithm, just added the best feature one at a time. And on Wednesday and Friday, we're going to talk about some types of regularization, and it'll be more thinking about complexity penalties. So see you Wednesday.